Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our December 2021 webinar, Long Distance Distributed Fiber Optic Sensing. This is a presentation of FOSA's Technology Committee, which is really one of the most active committees within the association and has done a breadth of really good work. But we're very pleased to have our current chairman, has been chairman for the last year, Wayland Hill of NKT Photonics, to do a presentation on a topic that is frankly one that comes up with some regularity, at least as a question, which is how long can sensing operate? What are the maximum distances? And so this is a great opportunity to drill down on this particular topic. So Wayland, we very much look forward to your presentation.
Mike, thanks a lot for your introduction. In my webinar on long distance fiber optic sensing, I will first give you a short introduction into Fiber Optic Sensing Association, and then I will explain a bit the basics of distributed fiber optic sensing and its applications. The main part of the webinar is dedicated to technologies enabling long distance, and I will also show some data from lab demonstrations and from case studies in the field. The Fiber Optic Sensing Association, FOSA, is a non-profit organization promoting the use of fiber optic sensing technology. It was founded 2017 in Washington and has currently 24 full members and 5 consultants. We are educating industry, government, and the public on the benefits of fiber optic sensing. We provide information on the use of fiber optic sensing to secure critical facilities, enhance public safety, and protect the environment. We do this by giving webinars, writing white papers, recommended practices, by public presentations, and also by public policy advocacy. We furthermore publish a monthly newsletter called The Monitor, and the main work of FOSA is done in the Technology, Public Policy, and Smart Cities Committees, and this is a joint presentation of the members of the Technology Committee. If we look at the basics of distributed fiber optic sensing, DFOS interrogator basically consists of a laser and a detection system. And the laser sends short light pulses into an optical fiber where there are no sensors, but part of the light is scattered back and detected by the interrogator. As the localization of signals is achieved by looking at the travel time within the fiber, and this is very similar to a radar system. In the fiber, we have basically 3 main scattering effects which are used for distributed fiber optic sensing, which is the inelastic Rayleigh scattering, which does not change the wavelength or frequency of the light. And then we have 2 inelastic scattering processes, the so-called Raman and Brillouin scattering. Both change the wavelength and the frequency. Raman scattering much more than Brillouin by about 13 terahertz, whereas Brillouin shifts the frequency by 11 gigahertz only. The system analyzes different measurements for each scattering process. For instance, for Raman, it looks at the amplitude of anti-Stokes and Stokes signals. For Brillouin, it can look at frequency and also amplitude, and for Rayleigh, on amplitude and phase of the light returning to the system. And those measurements are related to physical parameters in the environment of the fiber, such as temperature, strain, and also dynamic strain and temperature. And those effects are used in different distributed fiber optic systems, namely distributed temperature sensing, DTS, distributed strain sensing, DSS, and distributed acoustic sensing, DAS. Distributed temperature sensing utilizes Raman or Brillouin scattering to measure temperature profiles. Raman DTS looks at the amplitude ratio of anti-Stokes and Stokes signals and has a sensitivity of about 0.3% per degree Celsius at room temperature. The Brillouin DTS looks at Brillouin frequencies and sometimes also on intensities. And there are two flavors of Brillouin DTS. One is using spontaneous Brillouin scattering. The technology is then called Brillouin Optical Time Domain Reflectometry, BOTDR. This is just using laser pulses in a single fiber. And then we have the stimulated Brillouin scattering called Brillouin Optical Time Domain Analysis, BOTDA, which uses two contact propagating lasers in a fiber loop. The sensitivity in both cases is about 1 megahertz per degree Celsius. And for the amplitude, it's very similar to that of Raman scattering. Comparing Raman and Brillouin DTS, we can say that Raman DTS is mostly more economic and it's also insensitive to strain. Brillouin DTS has stronger signals and can therefore provide a longer range. Distributed strain sensing, DSS, uses Brillouin scattering to measure strain profiles, and the technology is exactly the same as of the Brillouin DTS. So we here look mainly on Brillouin frequencies, and we again can use the spontaneous Brillouin scattering in a single fiber or the stimulated Brillouin scattering in a fiber loop. Distributed acoustic sensing, DAS, utilizes Rayleigh scattering or even reflected signals to measure dynamic fiber length changes related to vibration or acoustic events. This Rayleigh scattering provides the strongest scattering signals, but in contrast to the DTS and DSS systems, there's no time averaging possible when we want to record dynamic signals originating from acoustic events. It also requires a quite complex real-time processing of huge amounts of data. The measurements of DAS are amplitude for event detection and phase for quantitative measurements and frequency analysis. When we look at long distance, we have to consider that the frequency that can be measured is limited by the travel time of the light pulses within the fiber. And this results in a limit of about 500 hertz at a distance of 100 kilometer, whereas at shorter distances, for instance, at 1 kilometer, the systems can go up to 50 kilohertz. The sensitivity to dynamic strain is extremely high, and typically it's below 1 nano epsilon. The characteristics and benefits of distributed fiber optic sensing are that you can monitor long fibers in optical cables from a single location. This is done 24/7 continuous and in real time. Thousands of sensing points can be monitored using a single system. You achieve high spatial resolution and precise localization of events. In the application, you have just a passive fiber optic cable, and there's no electricity, no sparking in the application area, and the fibers are immune to electromagnetic interference. The systems measure temperature, strain, and/or acoustics. There are no discrete sensors in the field, and therefore there's no need for sensor communication network. Compared to thousands of individual sensors, the systems are highly reliable and often they do not require any maintenance. And for large assets, distributed fiber optic sensing is the most economic and sometimes also the only solution to monitor the whole asset. The main application areas of this DFOS are pipeline condition monitoring, third-party intrusion security, geotechniques, transport monitoring, oil and gas in-well monitoring, industrial process monitoring, structural health monitoring, and power cable monitoring. In this overview, I marked the application areas which are important for long-distance systems with yellow circles. And in the next slide, you see more detailed applications for each of the systems in all those application areas. You see there are lots of different applications for DFOS systems in the different application areas. And I cannot explain all of them in this webinar, but there are many other webinars of FOSA available where you can get more detailed explanations on all these applications. If you look on the history of the distance range of DFOS products, we see a tremendous increase. We started in the 1990s with a distance range of 1 to 4 kilometers, and then in the early 2000 years we came to 15 kilometers, not much later to 30 to 40 kilometers. In 2015, the first 70-kilometer systems have been available, and since 2018 we have 100 kilometers. The benefits of having such long distance ranges available is that the technology is very economic for large objects, and it also can cover large distances without power. And in some applications there's no power available, so in this cases it's also the only solution to monitor such assets. What limits the distance range of DFOS systems? First, we cannot launch as much laser intensity or power into a fiber as we want because it's limited by nonlinear effects. Then we see a continuous attenuation of the signals over distance because of the loss in the optical fibers. At some point, this results in a very weak signal, where we see the granular structure of light and causes shot noise, and this limits the distance range. Looking at the interrogators, there's another limit, which is the optical loss budget of an interrogator. And this lost budget, in comparison to the fiber loss, determines the distance range where such an interrogator can be used. Of course, ideally, the interrogator has such a high loss budget that it reaches the shot noise limit. The next section of the webinar deals with the enabling technologies for long-distance DFOS. First, we have to look at the loss in the fibers. The first DFOS systems operated at a laser wavelength of 1064 nanometers, and at this wavelength, the attenuation in optical fibers is pretty high, around 1 dB per kilometer. Later on, we switched to 1550 nanometers, and there the attenuation is 5 times lower, around 0.2 dB per kilometer, which results in a corresponding extension of the distance range. Furthermore, research on better fiber materials goes on, and this leads to lower attenuation in commercially available fiber products. Now, some submarine telecommunication fibers are available which have attenuation of 0.15 dB per kilometer only. Then, of course, we can try to launch larger laser energy into a fiber. As I already said, the laser intensity is limited by nonlinear effects, but we can even launch larger energy by using longer pulses. Then we have more energy at the same intensity, but this, however, compromises spatial resolution. There are also some parameters where the fibers can be improved. For instance, large mode field areas allow for larger power at the same intensity, and current ultra-low loss submarine fibers have a mode field area of 150 square micron, which is about twice that of standard single mode fiber. You also can use negative dispersion fibers, and then we have no modulation instability, and higher intensities are allowed. Especially for distributed acoustic sensing, engineered fibers are pretty useful. The ultra-low loss fibers already mentioned are optimized for low Rayleigh scattering, and this also results in lower distributed acoustic sensing signals. One idea to enhance the signals is to use enhanced backscattering fiber at the far end of an ultra-low loss fibers. Then you get higher signals at the outer end of the whole fiber length. And another comparatively new technology is to use additional point reflectors in the fiber, which are generated by femtosecond laser pulses. Those point reflectors are pretty efficient because they direct the light back and do not scatter in all directions. So they can generate a large signal with a low additional attenuation. And by proper design of those reflectors, you also can avoid interference fading, which is an issue in distributed acoustic sensing. Altogether, such fibers can result in a large gain in signal and distance. Inside the interrogators, there are also some important technologies increasing the distance range, and one is coherent detection. Coherent detection means that you superpose the signal coming back from the fiber with some light from a local oscillator, which can be the same laser generating the pulses or also another laser. By this superposition, you get a signal which depends on the square root of the product of the powers of the local oscillator and the signal itself. And because the local oscillator can be very strong, this gives a strong increasement of the signal. The square root also reduces the dynamic range and makes it easier to measure larger distances. Altogether, this technology increases clearly the optical budget. Correlation or so-called pulse coding techniques are another possibility to increase the distance range of interrogators by launching more laser energy. The laser pulse length is normally corresponds to the spatial resolution of the system, which is very short in the order of meters, and the pulse interval is determined by the fiber length. And of course, this results in a very low duty cycle in the order of 10 to the power of -5 for very long fibers. And this approach here is sending coded laser pulse sequences into a fiber and then to decode traces using the coded sequences in order to regain response corresponding to that of a single laser pulse. And the signal gain achieved here, signal to noise gain achieved here, is proportional to the square root of the code length if the system is limited by the detector noise. Another technology in the interrogators is antifading for distributed acoustic sensing. In acoustic sensing, highly coherent lasers are used, and when you look at Rayleigh scattering, there are multiple scattering centers within the fiber, and you see a kind of interference of the light coming back from all those scattering centers, and depending on the phase and the polarization of the light, the signals vary very much. You see this in the right trace. This strong signal variation here is no noise. It's a result of fading. And of course, this fading reduces the distance range of a system. And fading can be reduced or even eliminated by using multi-wavelength techniques, multiple lasers or swept frequencies, polarization, diverse detection, and engineered fibers with reflectors. We also can look at remote components to help increasing the distance range. And one possibility is optical amplification in the field. This means, for instance, that you have interrogator and pump laser at the site where you have electrical power, and then you have different fibers for sensing and for pump light. You combine both, and then you have a piece of active fiber in the field, and then in this active fiber, the laser pulse and the returning signals are amplified. There are different configurations possible. You can use multiple remotely pumped optical amplifiers. You can use distributed amplifiers using the Raman effect. And you can also use electrical pumped erbium doped fiber amplifiers in the field, or even combined schemes. There are, of course, some limitations, because when you look at ROPAs, the pump light is also attenuated, so this limits a bit the distance range, and the amplifiers add noise. And finally, if you want to pump remote components with electrical power, this is also required in the application. The last technology I want to mention here is the use of circulators for distributed acoustic sensing. Normally, the circulator is integrated in the interrogator, but if you move it out into the field, then you have passive transport fibers for the laser pulse and the signal, and just a shorter piece of sensing fiber. Of course, the transport fibers are then not monitored, but the advantage of this setup is that it enables higher repetition rates because this is only determined by the length of the sensing fiber, and therefore you have a higher duty cycle and thus more laser power in the fiber, and you can monitor higher acoustic frequencies. A typical application of this setup is topside interrogation of subsea wells. Now we come to some data obtained in lab demonstrations. The first is long distance BOTDR DTS using Raman amplification and pulse coding. With this technology, 120 kilometer distance range has been achieved with a pretty good spatial resolution of 5 meters and a temperature resolution better than 2 degrees. This is a BOTDR-A DTS with a cascaded point amplification. This is a setup very similar to what is used in telecommunications. Here, a number of cascaded amplifiers are used, which are supplied with electrical power. So, of course, you can use this where you have electrical power. And what you see here is that a very high distance range has been realized of 330 kilometers, and the temperature repeatability is very good over the whole distance. So you see it, the repeatability or resolution of temperature increases with distance, but then almost the original resolution is regained after the amplification. And the spatial resolution of this setup is also very good with 3 meters only. This is a lab demonstration of a commercial system using BOTDR DTS technology. This system uses polarization diverse coherent detection, and because it's BOTDR technology, single-ended interrogation without amplifiers can be used. And this setup results in also in a pretty long distance range of 120 to 150 kilometers. And at 120 kilometers, 15 meter spatial resolution have been used, and the temperature resolution is below 2.5 degrees, and 2 hotspots at 75 degrees at 100 and 120 kilometer are clearly visible. With the 150 kilometer fiber stretch, you see that temperature resolution degrades when you go beyond 125 kilometers. But we just wanted to see how much we can achieve. This is a lab setup of a long distance quantitative distributed acoustic sensing system. It again uses the polarization diverse coherent detection scheme and standard single mode fiber. Phase and amplitude are analyzed, and on the lower left you see the sensitivity and dynamic range of this system at 70 kilometer distance. And the sensitivity is well below 1 nanoepsilon, and the dynamic range is larger than 4 orders of magnitude, and the dependency is pretty much linear. On the right side, you see a 100 kilometer measurement using standard single mode fiber, where we generated 50 nanoepsilon periodic event at 93 kilometers, And you can clearly see this signal with a very good signal-to-noise ratio. And even at 124 kilometers, an acoustic event generated by a speaker was been detected. In this case, 1 kilometer of engineered fiber with enhanced backscattering has been used at this position. The capabilities of commercial long-distance DFOS systems are summarized in this table. I want to show you here some typical data, no record data. So the distance range is determined by the availability of at least 2 commercial systems providing that range. And you see, and also we assume that no external amplifiers are used and only standard fibers. And in this case, you see that the Raman systems reach a distance range of 30 to 50 kilometers, whereas the other systems have a larger distance range. This is related to the weakness of the Raman scattering defect. Brillouin and Rayleigh systems provide a distance range of 50 to 100 kilometers, and all the systems have a special resolution, measurement time, and repeatability, which is very relevant for many applications. Now we come to the case studies. The main part of the case studies is related to offshore power and interconnectors. Power cables are more and more used in submarine environment because the increasing use of renewable energies requires the connection of grids of different countries because the renewable energies are strongly fluctuating. And also a large part of the power is generated in offshore wind farms. And there we have all the cables. First, the transocean interconnectors, which are typically more than 100 kilometers long. Then the wind farm export cables, which are 30 to 100 kilometers long. And then we also have interconnection cables within the wind farms. Those cables are normally pretty short, but if you want to monitor them from shore through the export cable, you also need long distance monitoring systems. And with the DTS, you can monitor the fiber temperature to identify hotspots in the cable. Then the core temperature of the cables can be obtained from those fiber temperatures using thermal simulations. And even the ampacity, so which means the current carrying capacity of the cables, can be predicted using the so-called real-time thermal rating software. And finally, it is also possible to look at the depth of burial of such cables using the thermal response of them. The distributed acoustic sensing systems can detect suspicious vessel traffic, anchoring, trawling, and also digging excavation. One further important application is the exact detection and localization of cable faults, because the repair is much easier if the precise localization of a fault is known. The first example is the monitoring of a wind farm export cable in the North Sea by DTS. So this is a field trial on a 50 kilometer long export cable where hot and cold spots could be identified, and when we look at the temperature profiles and high and low load, we see the load dependence of the temperature. And you also see some hotspots. 3 of the hotspots have been more or less expected because at those positions we have cable joints, and there's one unexpected hotspot which is clearly visible, and surprisingly the cable failed exactly at this position 2 weeks later. And this fault created not only several million euros of repair costs, but also a huge loss of electrical power production, because it happened in winter time where repair was not possible. So if this cable would have been monitored continuously, I would say that this fault could have been detected earlier, and planned repair would have reduced the cost considerably. There are also some cold spots, as I mentioned, and those are probably related to an insufficient burial of the cable in the seafloor. The Great Penelopolis interconnector is fully monitored by DTS, so it's a pretty long interconnector with a 100-kilometer cable route. In this case, BOTDA technology has been used with some amplifiers on land side at the end of the cable. So on the whole fiber stretch, there are no external components or amplifiers. And with the setup, pretty relevant and good performance has been achieved. So the measurement time is 15 minutes only, spatial resolution 5 meters, and the temperature resolution 1.5 degrees Celsius only. When you look at the map of the United Kingdom, you see that there are many interconnectors to other countries, and we have measured 2 of them using BOTDR technology, which is single-ended and does not require a loop. No amplifiers have been used, and only standard single-mode fibers. And you see 2 examples of a 70-kilometer distance and a 95-kilometer distance. The first one was measured with 5 meter spatial resolution, and the later one with 10 meter. And in both cases, you also see not only the temperature profiles, but also the temperature resolution curves over distance. And it shows that the temperature resolution is extremely good over this large distance. The Nemo Link HVDC interconnector is monitored by distributed acoustic sensing. This is a 140-kilometer long interconnector transmitting 1 gigawatt of electrical power. The fiber is even longer, 154 kilometers. And all this is fully monitored by using 2 DTS on both ends of the cable. And on the right, you see some acoustic signatures of waves and also rock dumping. And the main purpose of using DTS here is to identify potential threats resulting from TPI at landside, and also from fishing activities subsea. The second purpose of using it is to detect and localize potential cable faults. The Norway-Denmark interconnector cable, which is also pretty long, is monitored with DTS and DAS in combination from both sides. And in this case, we do not only have the applications that I already mentioned, but because this is DAS with low frequency capability, it can also measure a temperature gradient with high resolution. It's a combination of the absolute temperature and the temperature gradient from the DAS give temperature profile with very low noise or very high temperature resolution. Distributed acoustic sensing has been used for highway monitoring in Tenerife. This system uses a 100 kilometer distance range with 10-meter channel spacing. And in the upper picture, you see many traces related to the traffic. Traces can be by car, can be caused by cars or by lorries or any kind of traffic, and the inclination of the traces is caused by the velocity. So you can analyze velocity of the traffic flow in general, but you also can analyze the condition of the roadways. And the last example I want to show here is earthquake detection by long distance DAS. This is a 100 kilometer distance system in California, and there was an epicenter 90 kilometers away from the fiber. And on the upper picture, you see lots of traces related to traffic, and then at a certain time, you see the arrival of the S&P waves from the earthquake, represented by almost horizontal lines. And in the lower picture, you see a filtered picture where a low frequency bandpass has been applied, and there the earthquake traces are much better visible. Summary of my talk is that new technologies enable long-distance distributed fiber optic sensing, and the distance range of commercial interrogators increased from about 1 to 4 kilometers to about 30 to 100 kilometers. I've shown data from lab demonstrations beyond 100 kilometers, and I think I have shown that there are important applications in pipelines, transport, intrusion detection, and power transmission. I want to thank Etienne Rochard, Chris Minto, Alex Diode, and Torben Jostmeier, who all contributed their data to this presentation. And now it's time for questions. You can ask your questions now, send it to Mike. But I'm afraid there's not enough time to answer all questions now, and you even can send your questions by email. The email address is shown at the end of this presentation. Thank you.
Thank you, Wieland, and thank you for a very informative presentation. We actually have a cluster of related questions, and so I'll try and kind of combine them all together. And they kind of revolve around the issue of what are the limitations of using optical amplifiers. Sort of, I think people are looking for ways of sort of what are the outer limits and what could be done to extend distances.
Yeah, so amplifiers are very useful to extend the distance range. I have shown data for up to 330 kilometers. Of course, there are limitations because first, amplifiers must be available in the application. So sometimes it's difficult to install amplifiers when you come with your sensing system, because maybe the power interconnector cable has been installed years before where nobody thought about amplifiers. If the amplifier is there, you need to provide some energy to pump it, and this can be done optically, as I explained, but it can also be done using electricity, but in this case, of course, you need electricity in the field.
So, I mean, and following up on that, is there a fundamental limit to the distance of DFOS? I hesitate to ask the question because you'll probably come up with a way to exceed that, but is there a theoretical limit?
Yeah, so it's a very good question, but the answer is not that easy. If you look at a certain setting, for instance, you say there are no external components in the field, no amplifiers, just standard fibers, then and you want to measure events with within a certain time, with a certain resolution, then there are fundamental limits, and I think the current interrogators are very close to reach them. But if you allow for more components, technologies in the field, or if you relax the requirements for resolution, then the range can be further extended.
Here's one. Has anyone examined the Fenton reaction problem that exists within many fibers?
What reaction?
Fenton?
I don't understand. Maybe we do this by email.
Yeah, I'll ask that questioner to follow up with you directly. Could you talk a little bit about some of the applications that sort of long distance fiber are opened up as a result of being able to extend the distance? You've obviously talked about those that are in the sea or in the ocean. Are there other applications along the same lines that are sort of enabled because of being able to expand the distance quite so far?
Yes, sure. I think most important is pipeline monitoring, because pipelines are sometimes even much longer than power cables. There are some oil and gas pipelines which are more than 1,000 kilometers long, and there's first, it's more economic to use a lower number of systems covering each larger distance, but also the pipelines go through rural areas where there's no electrical power available, and this also makes it necessary to monitor a large distance. Then, when we look at oil and gas offshore wells, those wells are typically not so deep in the range of 1 to 5 kilometers mostly, but the wells are maybe at large distance from shore, and it's more convenient to interrogate them from shore. And furthermore, at the wellhead, there are some feed-throughs and connectors with pretty high attenuation. And this is also something that makes the use of long-distance systems with high optical budget necessary. And then also when you look at borders, and they also go to remote areas where you don't have power and want to monitor large distances with few systems.
I'll share with you the comment. It's not a question, but the comment of one of our audience members whose point is that there's no limit to range. 4,000 kilometers is possible. So
yes, yeah. of course, that's an opinion. I'm a bit careful. Of course, when we look at telecommunications, we see that transatlantic transmission is possible, but sensing systems are a bit different, and what we need to do is to demonstrate that it really works. So we can think that it could work, but at the end, we need to see some data.
That's a fair point there. I'm going to ask, I think, a compound question. So one is can you detect corrosion events within pipelines? And I may ask that just a little bit broader than that, is as you expand distances, is there a degradation in the ability to detect some events?
Of course, there's a degradation of resolution, temperature, strain resolution, or also resolution of dynamic strain. So, and also sometimes spatial resolution needs to be compromised. So some of the weaker events may not be detectable at large distance, which can be easier seen at shorter distance.
Along the same lines, is where do you see the future of the technology advancing? Longer distancing or more precise signal processing, or some combination of thereof?
I think there are different directions. So today I talked about long distance, which is one important development in distributed fiber optic sensing. But there are also very different applications where you look at better resolution. For instance, when you monitor industrial plants, there you want to look into details of your installation, which are sometimes pretty small. And this creates a wide range of different products and uses of such systems.
So here's an application-related question. I hope you are there applications for using DFOS for monitoring vortex-induced vibrations in submarine cables with free spans?
Yes. So I was not able to talk about all the uses of DFOS, even not in power cables. But of course, there are investigations on using the systems for analyzing especially vibrations within those cables or movements in the waves. So all this is ongoing and developing. And for power cables, I would say it started with temperature monitoring and then fault detection and anchoring came across, but there are many applications that will be added in the future and are still in the initial phase.
Next is what are the point reflectors and how are they created within a fiber?
Yeah. So point reflectors are weak variations of the refractive index, which are created by nonlinear optical effects in the focus of a femtosecond laser. And the purpose of using such a short pulse laser and the nonlinear effect is that you can penetrate the coating of the fiber with the laser, so there's no need for uncoating. And so you can use standard optical fiber and add the reflectors every few meters, and that's it. Then you have the reflectors you want, and you can use it for distributed acoustic sensing.
So this is, I think, a related or follow-up question to that, which is that how does the structure of the fiber optic cable affect its acoustic sensitivity, and are there studies on the subject?
Yeah. So in contrast to temperature, which is conducted anywhere, the acoustic signals need to be coupled into the fiber. So the cable needs to be coupled to the environment, and the different layers of the cable also need to transfer the acoustic energy into the fiber. And there are different cable designs which work more or better or less good. I would not say that there are cables which are completely insensitive, but the sensitivity of cables is different, and there are also studies or systematic investigation on the dependence of acoustic signals on the cable design.
Next, and again related, is what is the impact on sensing functionality of fiber when it is inside a conduit?
Yeah, conduits are widely used to protect the fiber and to allow for easy replacement of fibers. For temperature measurements, I would say there's little effect because most of the temperature events that we look for are very slow, and there's enough time for temperature conduction into the conduit. When you look at strain, you need mechanical coupling of the fiber to the environment, and when you have a conduit with a loose fiber inside, then it will not work, of course. And for acoustic sensing, I would say that, of course, it has some influence on the sensitivity, but there are many demonstrations that acoustic sensing works well with fibers and conduits.
Next is, could you elaborate on the sort of what are the characteristics or what are the need for long distance interrogators for subsea wells? So maybe you can explain how those are different.
Yeah, I already talked about the subsea wells. One thing is that you may want to interrogate them from shore, and then you have a lead fiber from shore to the well, which can be several 10 kilometers long. So this is one reason for using long distance systems. And the other reason is that at the wellhead, the wellhead is tightly closed to keep the pressure inside the well. And at this position, you need some feed-throughs and also connectors, which normally have some optical loss, and you need to cover this loss with the loss budget of your system. And long distance systems have the higher loss budget compared to standard systems.
So I think this will be the last question, and this is really on, again, another fiber-related question. And you've described the use of sort of standard telecommunications fiber, the availability of that to do sensing. But could you kind of expand on how enhanced fiber can be used to enable fiber sensing, and how that may expand the range?
Yes, I think the best example of enhanced fiber is the one with the additional reflectors. And Of course, the additional reflectors generate little additional attenuation. So normally you would not use it for the full length if you want to reach a maximum distance, but you may start to use this engineered fiber from a certain point, and then it gives signal gain in the order of 10 dB or so, and this corresponds to additional distance range of several 10 kilometers.
Well, thank you for that. I'm afraid that we're at the top of the hour. As you mentioned at the outset of the questions, you're available to answer questions by email. And we also had a number of questions about when this presentation will be available. Of course, all our presentations are available on the YouTube channel that we have, and certainly recommend folks to take a look at that. And obviously, it's available to share with colleagues who may have not been able to participate. So Wieland, thank you very much. We really appreciate you and the Technology Committee for a very informative presentation. And that concludes this FOSA webinar.
Thank you. Goodbye.